In this video, we're going to learn how to use differentiation to determine the intervals on which a function is increasing or decreasing. So for our first question, we want to find the values of x for which the function f of x equals 3x minus x cubed is increasing, and then we also want to find the values of x for which the function f of x is decreasing. Now, both of these things we want to do, find where it's increasing and find where it's decreasing, they both boil down to looking at the derivative. The derivative represents the rate of change or the slope of the function, so a positive derivative means the function is increasing, whereas a negative derivative means the function is decreasing. So the very first thing we want to do is compute the derivative. We're given the function f of x, it's equal to 3x minus x cubed, and this is pretty straightforward to take the derivative. F prime of x is equal to 3 minus 3x squared. Now to find where the function f is increasing, we want to find where the derivative f prime of x is positive, where it's greater than 0. So subbing in the expression for f prime of x, we have 3 minus 3x squared is greater than 0. We can simplify by dividing out by 3, get 1 minus x squared is greater than 0. Let's move the x squared to the other side, get 1 is greater than x squared, and flip it around so it's easier to see. X squared is less than 1. Then we can apply the square root. So square root of x squared is less than square root of 1. And square root of x squared is absolute value of x, while square root of 1 is 1. And if absolute value of x is less than 1, that means that x has to be greater than negative 1 and smaller than positive 1. So that means f of x is increasing on the interval from negative 1 to 1. Now let's find where f of x is decreasing. This is going to be a similar process. We still look at the derivative, but now we want to tell where is the derivative negative. So we sub in our expression for the derivative, 3 minus 3x squared. We want to find where that's less than 0. Now the steps here to solve this equation are really just the same as the steps we did over here. The only thing that changes is the sign is flipped. So why don't we skip all the way down to this final step where absolute value of x is less than 1, and here it'll be absolute value of x is greater than 1 because the sign was flipped. And if absolute value of x is greater than 1, then that means either x is greater than 1 or x is less than negative 1. X is greater than 1 corresponds to the interval 1, infinity, and x is less than 1, and x is less than negative 1 corresponds to the interval negative infinity to negative 1. So our final result is that f of x is decreasing on the union of those two intervals. We'll put the left interval first, so negative infinity, negative 1, union 1 infinity. And there we go. There's our final result. Here's another problem. We want to find the values of x for which the function g of x equals x squared minus 1, the quantity, times e to the x, is increasing. And then we also want to find the values of x for which g of x is decreasing. And like before, we're going to use the derivative to figure this out. So first step is to differentiate this function. Our function is g of x equals x squared minus 1 times e to the x, and we'll take the derivative. G prime of x is equal to, well, we've got to use the product rule, so derivative of this expression here, x squared minus 1, that's 2x, and then times our e to the x, and then plus that expression, x squared minus 1, times the derivative of the second term here, of e to the x, and derivative of e to the x is, well, just e to the x. And we can simplify this a little bit. We can factor out an e to the x from both of these, and then we've got x squared plus 2x minus 1. all that times e to the x. Now again, to find where g of x is increasing, we want to find where the derivative, g prime of x, is greater than 0. So subbing in our expression here for the derivative, we have x squared plus 2x minus 1 times e to the x has to be greater than 0. And wow, that looks like a difficult inequality to solve. One thing that we can do to simplify this inequality a bit is to notice that this e to the x term is always positive. It's never negative, it's never 0. It's always a positive number. So we are okay to divide out by e to the x. It's just like dividing by any other positive number. And if we do that, we get x squared plus 2x minus 1 is greater than 0. Which still looks like a kind of difficult inequality, but at least this one's a bit easier to solve. Let's think back to methods that we know for solving difficult inequalities. Whenever we're faced with a difficult inequality, we can remember that the solution to this inequality is going to be some intervals in the real number line for which this function here, x squared plus 2x minus 1, is greater than 0. On other intervals, this function x squared plus 2x minus 1 is going to be less than 0. So what we can do is we can find out where x squared plus 2x minus 1 is equal to 0, and that'll break up our number line into several different intervals, and then we can test each of those intervals to determine whether this function is positive or negative. We need to find where g prime of x is less than 0 anyway when we find where the function is decreasing, so it's not like we're doing any extra work. Let's draw a line here to separate these two steps to indicate that we're doing something a little bit different here. If we want to find where this expression is equal to 0, we might first try to factor the expression, but it doesn't look like it's easily factorable, so we can use the quadratic equation. So we can say x equals negative b is 2, plus or minus the square root of b squared, which would make 2 squared, which is 4, then minus 4 times a times c, so 4 times 1 times negative 1, which is negative 4. Then that's all over 2a, so all over 2. We can simplify that. Negative 2 plus or minus square root of 8 over 2, and 8 is just 2 root 2, so we've got negative 2 plus or minus 2 root 2 over 2, and that comes out to negative 1 plus or minus root 2. Alright, now let's use these numbers to break up our number line. So we'll draw a little number line here, and in this number line we'll label 2 points. One point will be negative 1 minus root 2, and the other point will be negative 1 plus root 2. Now this breaks up our number line into several intervals. First, there's an interval from negative infinity to negative 1 minus root 2. Then there's the interval from negative 1 minus root 2 all the way to negative 1 plus root 2. And then there's the interval from negative 1 plus root 2 to infinity. Now why don't we pick some test points for each of these intervals so we can tell whether g prime of x is increasing or decreasing at each of those test points. And whatever we find for those test points will apply to the entire interval. So first of all, let's choose a test point on the left here. What's a number that is left of negative 1 minus root 2? Well, how about negative 10? So at negative 10, we have that g prime of negative 10 is equal to negative 10 squared, so 100, plus 2 times negative 10, so minus 20, and then minus 1 times e to the negative 10. And that simplifies to 100 minus 20 is 80, minus 1 is 79, so 79 e to the negative 10. And e to the negative 10 is positive, 79 is positive, so this is greater than 0. And therefore, since our test point is positive, we conclude that the derivative g prime of x is positive on that entire interval from negative infinity to negative 1 minus root 2. Alright, next up, let's choose a test point in this middle interval between negative 1 minus root 2 and negative 1 plus root 2. The easiest choice there might be just negative 1, because we know that negative 1 minus root 2 is somewhere to the left of negative 1, whereas negative 1 plus root 2 is somewhere to the right of negative 1. So we'll choose negative 1 as our test point. And we compute g prime of negative 1 is equal to, Well, -1 squared, which is 1, then plus 2 times the -1, which is minus 2, and then that minus 1 times e to the -1. 1 minus 2 minus 1 is equal to -2, so -2e to the -1. -2 is negative, e to the -1 is positive, so the result is still negative, so g prime of -1 is less than 0. And therefore, this result applies to the entire interval. So g prime of x is less than 0 on this entire interval from -1 minus √2 to -1 plus √2. Alright, last interval over here. What's a test point on the right side of -1 plus √2? Well, how about 10? Positive 10. So we compute the derivative, g prime, of positive 10, and we get a result 10 squared, 100, plus 2 times 10, 20, minus 1, times e to the 10. 100 plus 20 is 120, minus 1 is 119, and that's times e to the 10, which is clearly greater than 0. So therefore, the derivative, g prime of x, is greater than 0 on that entire interval, -1 plus √2, infinity. And finally, we can write down our final answer. G of x is increasing on the following intervals. First of all, there's this interval here, -infinity, -1 minus √2, and then there's also this interval here, -1 plus √2, infinity. That's where the derivative is positive. And then g of x is decreasing on the intervals where the derivative is negative, which is just this interval here. -1 minus √2, -1 plus √2. So here we have it. There is the final answer. Now we know how to use differentiation to determine the intervals on which a function is increasing or decreasing. And in the future, we'll continue to learn applications of differentiation, such as using the derivative to determine local maxima and local minima.